Alrighty, ladies and gentlemen, boys and girls, back at it again with question 2 from the 2018 AP Calculus AB free response section. This is one of your 2 calculator questions, so we should have our handy dandy graphing utility fired up and ready to go. And let's see what it has in store. It says that a particle moves along the x-axis with velocity given by v of t is equal to 10 times the sine of 0.4 t squared all over t squared minus t plus 3 on the time interval between 0 and 3.5. The particle is at position x equals negative 5 at time t equals 0. Now, so this is giving us an initial point, an initial position, that at time 0 we are at negative 5. Which I know is a little confusing because the AP test does this sometimes. They use x for position. We usually used s in our class, but this is a time and a position. You'll see down here they're going to give you a second position particle, or a second particle, and they're going to give you the position as x sub 2. So don't be shocked if the AP test uses x as the position of a particle. Okay, so let's jump right in. Actually, before we jump in, let's enter this velocity function into our calculator. So y equals 10 times the sine of 0.4t, which we'll call x squared. Close that parentheses off, close the initial parentheses off, and then we're dividing that whole thing by x squared minus x plus 3. Now would be a good time to also make sure that your calculator is set to radians. You're going to get all sorts of issues if it's not. So you're in radians, all is well. And we've got our velocity function set up. Okay? So part A, find the acceleration of the particle at time t equals 3. I think we're actually going to have room on this just to do the problem down here. So recall that the acceleration is the derivative of the velocity. So the acceleration at time t equals 3 is really the derivative of velocity at time t equals 3. And before you get all your panties in a bunch and start trying to differentiate this using the quotient rule and all that stuff, this is a calculator problem. Let's use our calculator. So we've got this function. We can second quit. We can go to math 8 for our numerical derivative, and we're going to go d dx, our vars y1, and we want this for x equals 3, or t equals 3 in our case. Press enter. And so our velocity is negative 2.118. I guess I should have pointed this out before. There are no units given to us in this problem. Okay, so it doesn't say that time is in seconds, or time is in minutes, or that it's feet or meters. So this can be a unitless acceleration. So we can just box this up, and that's your point. It's a one-pointer. Cool. Okay, part B. Find the position of the particle at time t equals 3. Okay, so the position is not given to us. We are given the velocity, which is of course the derivative of the position function. And so in order to find the position at a given time, we're going to have to take the antiderivative of the velocity. But we're also going to have to be careful and recognize that our starting position is not at 0. It's at negative 5. So if we want the position at t equals 3, it's going to be our initial position plus the definite integral from 0 to 3 of vt dt. Because again, this is going to be the accumulated displacement, the net displacement, if you will, starting at 0 going to 3. Okay, because these are the instantaneous changes. So if we want the total movement, we'll just track those instantaneous velocities. Okay, and so for us, the initial position was -5. And we're going to add that to this definite integral to get our position at time t equals 3. Okay, this is much like, I think this was question 2 on 2019 as well. This initial position plus this accumulated change, this accumulated velocities is going to give us our current position. We'll see in a second that this is different. This integral right here is different than if we throw absolute values around here, where that's going to track the total distance of our particle that it's traveled. This one right here, because velocity can be positive or negative, is going to give you this net displacement where it's just maybe it moved right, maybe it moved left, maybe it moved right, but that's where it is. Okay. So again, we're going to go to our calculator. We're going to do -5 plus math 9. Now we're doing the integral. We're going from 0 to 3. Still using the, that glare is not helping anybody. Let's see if we do it. There we go, that's better. Vars, y vars, y1 in terms of x. And so our position at time t equals 3 is equal to 1.760. Now this is going to seem silly, but because the fraction or the decimal extends beyond this 0, you have to write it. 1.760 and 1.76 are not the same in the context of this problem, because 1.76 implies that that's just rounded off. This will keep going. So to get the point, we need the 0 in there. And so if we want to write that as a conclusion, we can say at time t equals 3, the particle is at position 1.760. And again, there's no units here. No units here, so we're not worried about units. This, I believe, was a 2-pointer. Might have been a 3-pointer, actually. Let's see. 3-pointer. You got 1 point for 1 point for setting up this integral, 1 point for recognizing the initial position, and then 1 point for your answer. 3 points. Okay, part C says evaluate the integral from 0 to 3 of v of t dt and evaluate the integral from 0 to 3.5 of the absolute value of v of t dt. Interpret the meaning of each integral in the context of the problem. Okay, so the evaluation part is, can you plug it in on your calculator? So let's do that first, because that's the easy point. Okay, you get 1 point for getting both of these integrals. So the first integral we want is that we're going to go from 0 to 3.5 of v of t dt. Straight up button mashing here. We'll go math 9 from 0 to 3.5 vars y vars 1 dx. Here someone is trying to reach me. No. Okay, and press enter, and we get 2.8, we'll call it 2.844. Okay, our second integral, which we care about, is from 0 to 3.5 of the absolute value of our velocity. The absolute value of our velocity. So we'll go into our calculator. It's going to look pretty similar. So math 9 from 0 to 3.5 again, but now before we do y1, we're going to go math num, and we're going to hit ABS for absolute value. Absolute value bars show up. Then we'll throw our y1 function in there. Evaluate this in terms of x. Okay, and what we're looking for is a number that is at least as big as our first integral. It cannot be smaller because this is tracking the total distance. These two numbers could be the same if it's always moving in the positive direction, but more likely than not, we'll see some change of direction, which will create a bigger distance traveled. So this integral should be a bigger number. And calculator's thinking, okay. And look at that, 3.737. So it is a bigger number, which kind of confirms our concept. So that is 1 point. Just getting those two, you get 1 point for both of those. The question is, how do we answer the second part? Interpret the meaning of each integral in the context of the problem. Okay. Here's how the AP test words it in the solution, and I like their wording because it's clean, but it's a little bit different than the wording that we've used. And so for this first one, and let's see how exactly we want to set up our answer. Let's say, so kind of off to the side. So the integral from 0 to 3.5 d of t dt is the net displacement. Okay, we said previously the position, which is not technically incorrect. It does measure our position, but it's a position relative to our starting time, which in our previous problem was 0, so we said position because that was accurate. But that's not always the case, as we see here, that if we don't start at 0, this is not our position at time 3.5. Our position at time 3.5 is -5 plus this number. And so the way we can say that to make the AP test happy is that this integral is the net displacement of the particle on the interval from 0 to 3.5. So in other words, relative to where we started at 0, we have moved 2.844 to the right. If this had been a negative number, it would have been to the left. Okay, so this is the net displacement on this interval, the relative new position from our starting position, or whatever our starting limit on the integral was. Okay, the second integral gives us something different. So with the absolute value thrown around, now every single velocity is positive. Every single velocity is positive. Okay, and so we know that that means this is going to tell us the total distance traveled by that particle. Total distance traveled by the particle on the interval between 0 and 3.5. And that is where your second and third points come from. However, with the scoring guide, you only get both points if you get them both right. You can't get one or the other. So it's a 2-pointer, all or nothing. Okay, and this concept of the relative displacement or the net displacement and the total distance traveled is going to keep popping its head up. So we got to kind of start to understand that difference. Okay, part D says a second particle moves along the x-axis with position given by x sub 2 of t is equal to t squared minus t for t between 0 and 3.5. At what time t are the two particles moving with the same velocity? Okay, well, so we're given a position, and they're asking us about velocity. Well, velocity is the derivative of the position, so probably our first step is going to be, let's take the derivative of this position. So x sub 2 prime of t, oh, I guess you can't see that, is going to be 2t minus 1. And in order to determine when this particle has the same velocity as our initial particle, we need to set their derivatives equal to each other. In other words, we want to know when is x sub 2 prime of t equal to v of t on this interval. Okay, well, we've got a calculator, and we can figure that out. So we go to y sub or our y equals. We've already got this one set up, so we're going to set up the second function, the derivative of the second particle, which is 2x minus 1. Go to our window. Oh, yeah, that's way off. Let's do an x min of -5, x max of, actually no, let's do like -1 and 5. The y min we can do like -10 and 10, scale by ones. Let's see how that does for us. Oh, way too much y. Way too much. Well, not way too much, but probably too much. Yeah, let's stretch this out a bit. Let's do the window, I don't know, -5 to 5. That'll be better. There we go. Cool looking graph. And we want to know where that red line crosses that blue sine wave. And so we go to second trace. We want an intersection. First curve, second curve, sure. And the intersection is 1.57054. So t equals 1.57054. So our conclusion will be that the two particles are moving with the same velocity at t equals 1.571. And again, there's no units here, so don't default into saying seconds. I don't know if they would be petty enough to mark you off for that, but they might. So leave it unitless because we do not know what the units are. That was a 2-pointer. You got 1 point for establishing this relationship that these two things need to be equal. And then you've got a second point for getting the right answer. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's your 9 points. And that was question 2 from 2018 AP Calculus AB pre-response section. See you later.